First, exactly what is a rigid basis? So, let's write down the definition first. A rigid basis is a bunch of n basis vector fields with a very specific property. The property that if you were to express the metric components in that basis, that is, of course, given by the metric tensor G, acting on the pair of vectors EI and EJ vector fields, the function that you get are constants. So each of these functions, Gij, are constant functions. If that happens, then you call your basis a rigid basis. Now, certain special things happen if you are using rigid basis, which makes life easy. On the other hand, certain other things don't happen. For example, the formula that we relied on to calculate the gamma mu nu lambdas, or gamma ijk's as the case may be, nu lambda d tau equals 0, this formula no longer works in any basis other than the coordinate basis. So you cannot read off the gamma mu nu lambdas in this particular basis just by looking at the geodesic equations. The simple approach that we had taken before. Also, of course, this formula, okay, let's go back to gamma ijk's that we used before, half g I l jk comma l with jk comma l, this Christoffel symbol of the first kind being combination of the derivatives of the metric components that we had written down before. This is not really available to you because these again give you results for coordinate basis. So first thing that we have to learn is how would a rigid basis change these issues. And here I'm going to just state the results without the proof. Once again, you can look up the proof in Castillo's book or some other advanced differential geometry book. Or if you prefer, you can wait for as and when I get to make videos on that. But let me just give you the results. One of the first results that you will get if you are using this basis, which essentially follows from the fact that now that the jk's are all constant functions, the vector fields acting on them gives you 0. You couple this with the definition of a connection and you can show that what this leads to is this result. Gamma ijk plus gamma jik equals 0. These are the conditions that you have on connection coefficients. But important thing is, what are these gamma ijk's with lower indices? This is of course the index lowered version of the gammas that we have been dealing with so far. So once you lower this index L using the metric, these functions that you get, they obey this antisymmetry relation that if you interchange I and j, you get a negative sign. We will next need a way to replace this expression, which of course is valid only in the coordinate basis. It turns out that if you use the fact that a connection that you're going to use in Riemannian geometry is metric compatible, that is grad x gij is going to be 0 for all vector fields x, what you're going to get is the following expression. Gamma ijk, these lowered index Christoffel symbols or connection coefficients, is going to be a combination of this kind. Plus gamma j ki minus gamma k ij. Of course, what exactly are these with square brackets? Now that's a pretty standard notation. Gamma I jk is half of gamma I jk minus gamma I kj. By the way, in the coordinate basis, these terms are actually 0 because you end up with a symmetry between the jk indices. Here you don't have that symmetry. Of course, the reason why you had a symmetry in the jk indices in the coordinate basis was because the torsion was 0. Here, torsion is still 0. We are still dealing with Riemannian geometry, but it does not translate to the result that this quantity vanishes. Instead, it is this quantity which can help you to reconstruct gamma ijk. If you think about it a bit, this is sort of reminiscent of the kind of combination of partial derivatives that you use to construct this quantity. And just note that the idea here is also the same. You cyclically permute ijk's. Two terms will come with a plus sign. The one with the minus sign is the one in which the third index k appears at the beginning. Just remember that, and it's really pretty easy to remember this formula. The final step that we need to talk about is exactly how do we calculate these quantities. And this is where Cartan's first structure equation, which we had no occasion to use so far, comes on its own. Now, let me remind you that Cartan's first structure equation essentially was this. It was about the torsion one form. And we did not pay any attention to that in the previous calculation because the torsion has all components 0 and therefore Ti is definitely 0. And if we were using a coordinate basis, the fact that Ti would work out to be 0 turns out to be rather trivial. However, if you look at what we have in this case, Ti is d theta I plus gamma ij wedge theta j. This is, of course, Cartan's structural equation, number 1. This tells you something about the gamma ij's directly, or rather, about these combinations. Note that we know that because we are dealing with Riemannian geometry, the Ti's have to be 0. But that tells you that the d theta i's, the exterior derivative of the one forms which form your covector basis fields, is given by minus gamma ij wedge theta j, which is gamma I jk theta k minus, of course, wedge theta j. This is nothing but the definition of the gamma ij's, the connection forms. But now you can just use the antisymmetry here to rewrite this as gamma ijk theta j wedge theta k. Now this might seem like a great thing because after all you know your covariant basis vector fields and then you just do an exterior derivative. These are one form, so their exterior derivatives are two forms, and if you expand the exterior derivative in the standard basis, you immediately get the gamma ijk coefficients. However, things are slightly trickier than that because the fact that theta j wedge theta k, this wedge product, is antisymmetric tells you that you can only get the antisymmetric combination of gamma ijk's out of this. Antisymmetric in j and k, that is. By the way, let me just remind you that if we were using the coordinate basis, the theta i's would actually be dx i's, and d of d's is always 0, so this side would vanish. And there, the right hand side would also vanish because there, the gamma ijk's would be symmetric in j and k. If you contract that with something which is antisymmetric in j and k, you're definitely going to get a 0. In this case, for a rigid basis, that's not going to happen in general. And what you can see is this is going to be given by theta j wedge theta k. This is simply a case where I've interchanged the nomenclature for j and k, that is called jk and kj, and then also swapped the theta k wedge theta j back to theta j wedge theta k to get a minus sign. And therefore, this is the same as half of gamma ijk minus gamma ikj theta j wedge theta k, or as we have just defined, there is gamma I jk theta j wedge theta k. So these quantities, of course, can be obtained from these by simply lowering the index, but these quantities can be easily read off from d theta I. So, our plan would be use d theta I to figure out what these coefficients are, lower the index, then form this to form the gamma ij case. And then, now that we have all the spin connections, our job would be to calculate the connection one forms and then go ahead from that. But the antisymmetry that we talked about makes our life a lot easier here too. Note that our gamma ij's were defined to be gamma ijk theta k, of course summed over k, or by lowering the index I, we can immediately write down this as gamma I j is gamma ijk with all lower indices theta k. But note that you have antisymmetry in I and j. So gamma ji, which by this definition should be gamma jik theta k, is simply minus gamma ij. So we have this obvious antisymmetry. Gamma ij is minus gamma ji. Not only that, if you use the Cartan structure equation, curly rij is d gamma ij plus gamma ik with gamma kj, and lower the index here to rewrite this as d gamma ij plus gamma ik with gamma kj, then you can immediately show that curly rij also has the same antisymmetry. That's trivial to show by just interchanging I and j here. The only thing that I need to worry about here, perhaps, when you go from the raised index version for the Cartan second structural equation to this version, is that you are actually doing a d here on gil gamma lj. Right? That is what gamma ij is. However, g's here are constant functions. You are using a rigid basis. So you can move the g in and out with impunity, and therefore this derivation is perfect. So what you have are gamma ij's and rij's, both having an antisymmetry, and therefore the number of gamma ij's that you have to worry about becomes a lot less. Now we will illustrate the working of this idea by making use of the same problem that we had talked about before. We will use g equals dr cross dr by 1 minus kr square plus r square d theta cross d theta plus r square sine square theta d phi cross d phi. And we will first try to find the rigid basis in which this metric becomes a constant. That is, the components of the metric tensor becomes constant. The metric itself is, of course, independent of the basis you choose. When I'm saying metric comes constant, I'm actually oversimplifying the statement. It should be the components of the metric becomes constant. And then go ahead and do the calculation, starting from that. Well, I can immediately write down this as theta 1 cross theta 1 plus theta 2 cross theta 2 plus theta 3 cross theta 3, where our thetas, the covariant basis vector fields that we will use now, are simply the following. Theta 1 is dr by root over 1 minus kr square. Theta 2 is r d theta. Theta 3 is r sine theta d phi. And in this particular choice of basis, which is going to make the G look like this, the components for G are, of course, trivial. They are just 1, 0, 0, 0, 1, 0, 0, 0, 1. And because here G is the unit matrix, raising or lowering an index does not change anything. So even the raising lowering part It's pretty trivial here. Now, for the actual calculation, we need to calculate exterior derivatives of theta 1, theta 2, theta 3, form the two forms and read off the gamma I square bracket jk's from there. Well, the only one which might seem to be slightly difficult is this one, but here calculating d theta 1 is actually very trivial. Note that the function in front is a function of r alone, so I don't even have to bother differentiating it. I know its total derivative is going to be something to do with r times dr, and that wedged with dr will give you 0. So d theta 1 is simply 0. d theta 2, that's trivial, dr wedged d theta. The only thing I have to remember is that you need to read off the gamma I jk's, but for that you need to express this in terms of the theta j's. Now dr d theta, well, dr is actually theta 1 times square root of 1 minus kr square, and d theta is theta 2 by r, so this really becomes square root of 1 minus kr square by r, theta 1 with theta 2. I apologize for the fact that I'm using theta for the covariant basis vector field and also using theta for a coordinate here, but I hope that will not lead to any confusion. And what about d theta 3? That's sine theta dr wedge d phi plus r cosine theta d theta wedge d phi. But once again, we need to rewrite everything in terms of the thetas, the theta 1, theta 2, theta 3's, and that is again rather straightforward. Plus cotangent theta by r, theta 2 wedge theta 3. So all the gamma I jk's that you want, all the non-zero ones, can be read off directly from here. In fact, it is easy to see that the only non-zero gamma I square bracket jk's that you can have are the following: gamma 2, 1, 2 from here, and of course gamma 2, 2, 1, that's not independent, so I'm not listing that separately. Gamma 3, 1, 3 from here, and gamma 3, 2, 3 from the last term. You need to exercise just a bit of care before you read this off. It might seem like this is given by root over 1 minus kr square by r, but you have to realize that when you say d theta 1 is gamma 1 square bracket jk theta j with theta k, you actually have two terms here. Gamma 1, okay, let's talk about gamma 2 because gamma 1s are anyway 0. Gamma 2, 1, 2, theta 1 with theta 2 plus gamma 2 square bracket 2, 1, theta 2 with theta 1, which essentially means is minus gamma 2 square bracket 1, 2 into minus theta 1 with theta 2. So the term actually doubles. It comes in twice, so this is actually half. The same thing can be easily used here. And this one is cotangent theta over 2r. Now, what we are going to do is use these expressions now to find out the non-zero spin coefficients. But you have to remember that our formula for that is gamma I square bracket jk is actually it's the other way around. What we want is gamma I jk is gamma I square bracket jk plus gamma j square bracket ki minus gamma k square bracket ij. Of course, cyclic permutation with a minus sign on the last term. And in order to use this, what we need to do is lower the indices on each of the three non-zero expressions that you have here. But of course, in this case, it's rather trivial because our G, the metric, is simply the identity. So the non-zero gamma 2 square bracket 1, 2 these are the non-zero terms. Gamma 2 square bracket 1, 2 and gamma 3 square bracket 1, 3 are both given by root over 1 minus kr square by 2r. It's the same as these numerically. And gamma 3 square bracket 2, 3 is cotangent theta over 2r with, of course, the corresponding antisymmetric counterparts, gamma 2 square bracket 2, 1 and so on. Now comes the job of figuring out all the gamma ij k's. Now, although I, j and k can take 3 values each, leading to apparently 27 values that we need to calculate for the gamma ij k's, the antisymmetry in the first two indices reduces our job a lot. The ij pair can only take 3 independent values, 1, 2, 1, 3 and 2, 3. And that reduces the number of calculations that you would have to do drastically. So, with gamma 1, 2, you can start with 1, 2, 1. And now you can easily see that what you are going to get is 1 square bracket 2, 1, which is 0. There are no first index 1 elements here. Then gamma 2, 1, 1, which is of course 0 because of the antisymmetry in the two indices in the square bracket. And minus gamma, again, 1, 1, 2, which also is 0. So this gamma 1, 2, 1 is simply 0. Gamma 1, 2, 2 on the other hand, has the first term gamma 1 square bracket 2, 2 which vanishes, but the second term is gamma 2 square bracket 2, 1 which is non-zero, which is a negative of whatever is written here. And then the third term is gamma 2, 1, 2 with a minus sign. And since these two terms are actually individually negatives of each other, when you subtract them, you get double the term. So you get minus root over 1 minus kr square over r. This 2, of course, cancels. Well, you can easily show that gamma 1, 2, 3 is 0 because there is obviously no combination of this kind which is out here with 1, 2 and 3, all 3 separate. Now, the next possibility for the first pair would be gamma 1, 3. 1, 3, 1. Again, you can easily show that the only possible non-zero terms would have been the ones with 1 in the front, but there are no such terms here. So there is 0. Gamma 1, 3, 2 vanishes for the same reason that gamma 1, 2, 3 vanishes. You only have to worry about gamma 1, 3, 3, which is non-zero because you get gamma 3, 3, 1 minus gamma 3, 1, 3, which is negative of the double of this. Well, with gamma 2, 3, there's a third possibility. In fact, when I said negative of the double of this, I meant negative of the double of this. So, this is wrong. It's minus root over 1 minus kr square over r. But with gamma 2, 3, by a very similar argument, the only non-zero term is going to be gamma 2, 3, 3. And that's going to be minus cotangent theta over r. So, of all our gammas, you have only a few non-zero elements. Gamma 1, 2, 2 is minus root over 1 minus kr square by r. When I say non-zero, I mean non-zero independent. Of course, gamma 1, 2, 2 being this means gamma 2, 1, 2 is plus root over 1 minus kr square by r. This happens to be the same as gamma 1, 3, 3. And in addition to that, gamma 2, 3, 3 is also non-zero. It's given by minus cotangent theta over r. Now, our job is to write for this basis the connection one forms.